Okay, hi guys, welcome back. Okay, today we are going to do sound 2, which is mainly on applications. So previously I learned about how waves behave, how they actually reflect, how they actually refract, what kind of law, mainly the law of reflection that they adhere to, how they move as with particles with reference to wave direction. Okay, so today we are going to look at application. So first thing first, what is echo? Echo is actually just over here. Hold on, sorry, give me a minute. Yeah, echo is actually sound reflection. Okay, so very simply, an echo, right, it will follow, it adheres to the law of reflection. Just like previously we learned in light, that light follows the law of reflection such that the angle of incidence, okay, if you have already forgotten, angle of incidence must be equal to the angle of reflection. Okay, so as is such, suppose I have a sound wave that's traveling from this point to the wall. So I do this, right, and therefore the sound wave will in the same way be reflected in this manner. And of course, if you were to draw the wavefront upon reflection, the wavelength should be the same. So this lambda here and this lambda here, let's call them lambda 1 and lambda 2. Lambda 1 must be equals to lambda 2. F1 must be equals to F2, and therefore V1 is still V2. Okay, so nothing changed. So even the angle of incidence and the angle of reflection are going to be the same. Okay, so on reflection only direction changes, that's all. Okay, so control quantity of echoes. Okay, so if it is so easy to reproduce echo, right, then why don't we hear echo everywhere? Okay, now one of the keyword here is high smooth wall. So this reflecting wall, it has to be smooth. Now remember back in the chapter of light, we learned something regarding diffusion. Okay, so we have a rough surface, so when light comes here, it will be reflected in this manner, but when light comes here, it will be reflected like this. I hope you all still remember something like this, right, because the normal are all at a different angle from this plane. Okay, this plane that I just drew in blue. Okay, so now it is the case, then this should apply for rough wall too. Now however, in a smooth wall, okay, everything is being reflected in the same direction. So yeah, that will make echo produce at a better rate. Okay, then therefore echo can be more prominent when it's being reflected by a smooth wall. Alright, so yeah, that's for the idea of echo. So for objects that doesn't have smooth wall, this includes things like carpets, this includes things like cloth. Okay, they don't have smooth wall, they have very rough surfaces. Okay, although they feel smooth, right, but to the waves they feel rough. Okay, and therefore it is quite difficult for them to reproduce echo in this scenario, right? So just a small understanding of echo. So first thing first, you can try example 1. Okay, so maybe you want to pause the video at this moment, try example 1 first, especially this question. I think it's a good question. Okay, I'll be covering this question in another video, particularly when I'm doing revision. Okay, so do think about this question, the one that I just circled in red. Yeah, so for the first question, it's quite simple. Okay, he heard an echo 0.5 seconds later, the sound traveled 1500 meters per second. So the total distance, okay, better right, total here is therefore 750 meters, right? You take 1500 times 0.5. Okay, so total distance is 750. Now this is an echo, right? So when echo, it needs to go down and then gets reflected. So if going down is considered as D, upon reflection it travels another D. In other words, 2D is equals to 750. So D will then be 375 meters. Okay, so how deep is the sea? The sea is 375 meters deep. Now, if the fish is actually moving at 10 meters per second, okay, there's no calculation involved here. But perhaps the next time I ask this question, I will set it as a calculation question. Now, if the fish is going to happen to move at 10 meters per second, you expect it to come to here, right? Now, so this is 10 meters per second. If this is the case, right, the fish might reflect the sound wave. Okay, if the fish is smooth. So this is one possibility. The second possibility, the fish might disperse the sound wave, and with that no echo will be heard. Okay, hence no echo. Alright, so yeah, quite straightforward too. Okay, now okay, so the uses of echo, one thing is to find the depth of the sea of locations. Okay, as with what we did over here. The other one is the detection of mines. So for the detection of mines, right, suppose this is my land, but I have mines here, right? So if I have mines here, okay, so what I can do, right, is, okay, sorry, yes, okay, so if let's say I have a ground and these are mines, the one shaded in black are mines, you know that they are of different density. So with different density you have different surfaces. Okay, so they might be reflected in a different manner. So if I have a scanner here, okay, it will produce sound, okay, and then it gets reflected back. Now when the scanner comes to here, it might produce sound towards here. It might get dispersed in this direction. So with this, I know that there is something underground here, and that it is possible that this is a mine. Okay. Now it is also true that echo, right, can be used by bats to detect water. Now for this, right, I need you all to check the link below. There's a very interesting video about how bat looks for water using echoes. Okay, so we call this I think it's something like this. I think this is how nature uses science. I think it's pretty cool, so do check it out. Okay, now determine speed of sound with echo. So this is quite simple. So suppose I have a source here and I have a very smooth wall, right? So all I have to do is I measure this distance as D. Okay, make sure that D is about 1 km or more would be best. Okay, now because of human reaction time, 1 km or more is good. Okay, so this source will produce sound waves and then it will be reflected. So this entire process, right, I time process. Okay, so you need to know that sorry, hold on, give me a moment. Is this not working? Okay, so you need to know that speed equals to distance over time. In this case, it will be total distance, which is 2d, over total time. So that's quite key. Okay, so speed is equals to 2d over t for echoes and okay, for echoes and when the time is taken at source. So this is the source, time starts here, it ends here as well. Okay, so as with such, as with the case, s equals to 2d over t. Alright, now we go to the next page and then we realize that yeah, so there are actually toys, right, that dogs play with. Okay, so you have this device here, and you have a pad, right? So yeah, whatever. Okay, something like that. Okay, so you have a pad. Okay, so and you have someone here. So this device, okay, actually is able to send out sound waves that dog can hear, but not human. Okay, we call this inaudible sound for us, but audible sound for the dogs. Okay, now the with regards to this, we'll discover what I mean when I say non-audible and audible frequencies. Okay, so basically the reason for this is because of frequency. So the higher the frequency or the lower the frequency, it actually affects our hearing. Okay, so first thing first, the frequency of a wave is the number of complete the frequency of a wave is the number of complete waves. Okay, hold on. Okay, as I was saying, sorry, I got cut out because there was some noise earlier. Okay, so the frequency of a wave is the number of complete waves it makes in 1 second, and of course the SI unit is hertz because it's discovered by Hendrik Hertz. Okay, we have watched the video. Okay, now sound above the upper hearing limit is called the ultrasound. Just like your EM wave, right? You have ultra UV ray, ultraviolet light. Okay, then sound below the lower hearing limit, we call it the infrasound. Okay, now give me a moment before I continue. I'll take a pause over here. Okay, now yeah, sorry, okay, some disturbance again. Okay, now so just like your EM wave, we have the visible light, then we have your infrared, then we have your ultra UV ray, right, which is your ultraviolet light. Okay, now so the word infra and the word ultra is being used here again over here, so I think it's quite simple to remember. Less than 20 Hz and more than 20,000 Hz. Okay, that's because for human, right, the detected frequency is 20 Hz to 20,000 Hz. Okay, this is the frequency that we can hear. Okay, sorry, I need to take a pause again, sorry. Okay, sorry about that. Okay, so let's finish this up. Audible frequency range decreases as people grow older, and that's why sometimes it's harder so sometimes it might be difficult to hear. Not on about noises, because noises happen within a certain range of frequency, but it is difficult to hear concerts perhaps by students, because when you are young your frequency tend to be higher, and because your audible frequency range decreases, it is actually a challenge to hear students sing, because the frequency of students are usually higher. Okay, for dogs, right, they are ultrasonic, so we say that dogs can hear above 20,000 Hz. Okay, and of course for bats it's below 20 Hz. Okay, so dogs hear ultra high frequency sounds produced by an ultrasonic dog whistle. Okay, so this ultrasonic dog whistle, right, it's not audible to human. Okay, now earlier when over here I talked about detection of water by bats. Okay, there's a term for this. Bats use this term, is called echolocation. Okay, now with regards to this, ultrasound cannot be heard, but it can be used for such as prenatal scanning. That means scanning for babies, right? Okay, there's a link below, so check out that link, and yeah, if you can fill up this box on how it works. Okay, now all these applications are useful because it actually may be tested, and I think it is good to know all these different applications as well. Okay, now so, and of course if we can use ultrasound, right, So you need to know that ultrasound is much less harmful than EM waves. Okay, in fact we can actually use EM waves, right, to do the scanning too, but we do not want that to happen because it is for this case, because ultrasound is much less harmful. Right, now we are near the end of the chapter, so yeah, before, alright, so yeah, please check the link below. Okay, now I'll continue with the idea of loudness and pitch. Okay, so I think I taught this in class before. Loudness got to do with energy, and energy has to do with amplitude. So with that, okay, yeah, actually going to the larger the amplitude of vibration, okay, the more energy it actually transfers, and the louder the sound. Okay, now pitch, the higher the pitch of a note, the higher the the higher the frequency of a note, the higher the pitch. Okay, so pitch has to do with frequency, while loudness has to do with amplitude. Yeah, please remember that. Okay, you can remember something like LAPF lah. I don't know what that stands for, but yeah, you can remember something like this. Okay, so maybe love animals, protect family, something like that. Yeah, such a peace-loving message, right? Okay, so yeah, just remember this. If this ever comes out, well, please, it's a bonus, so don't ever lose marks here. Okay, just a little bit more info. When I say amplitude is higher, this is how the wave transforms in terms of graph. Okay, changes, how it changes. Okay, so high amplitude will be, yeah, you all know. Okay, and low amplitude will be much lesser, the height here. Okay, as I noted over here. Okay, and for frequency, this is the number of waves. So this is T1, this is T2. You realize that T1 is here. So in T1, this completes about 2.5 waves. Now in T1, this only completes about 1 wave. Okay, so 1 waves. Okay, W means waves. Okay, so you realize that the higher the frequency, the more packed it becomes. Okay, so okay, now because I'm going to talk about pitch. Okay, so yeah, let me just transit to me strumming some guitar. Okay, and let me show you how pitch is affected. So in this video, we're going to talk about the guitar. Okay, and yeah, in particular, we're going to talk about the frequency and the pitch of the guitar. Okay, and so you understand better regarding pitch, frequency, as well as the strings. Okay, how thick or how long or how tight will actually affect the frequency. Okay, now before I continue on, okay, I'm gonna play a small part of this song called Viva La Vida by Coldplay. Okay, even to know roughly how the song sounds like, it's also in the link below. Okay, so I'm just gonna play. Okay, and I'm gonna play it twice. First with this thing over here. Okay, and second with maybe this thing slightly shifted, so that the length of string that I play with is now shorter. Okay, so I want you to hear the distinct, the difference, okay, between the first time I play and the second time I play, particularly in terms of its pitch, and then we'll link this to the idea of frequency later on. Okay, so give me a minute. Okay, and I'm back. Okay, so yeah, I'm gonna play the first time. Okay, and it sounds something like this. Okay, so yeah, that's yeah, and it just continues on. Okay, so that's the first one. We are now going to play the second one with this shifted down to here. Okay, so earlier it was here. Okay, and the length was from this finger all the way to this finger. The length of string that I play was this length. Okay, now I'm going to shift this down to this point so that the length at which I play in now is from here to here, and that is the length is now shorter. Okay, and I'm going to play the same chords. Okay, my left hand is going to play the same chords. Okay, the fingering, the position is all the same. Okay, but I want you to hear the difference in the sound. Okay, so it goes something like this. Okay, now I hope you all can hear the difference. Okay, there should be a difference. Okay, and yeah, let's go to lesson proper now. Okay, so the first thing that I want you all to discover was that is regarding the length of the string. So when this thing was here, the length was this, right? Okay, and let me just play the first string for you to hear. Okay, it sounded like this, but when this comes to this point, so that the length of string is now less shorter, it sounds like this. Okay, and in fact I can do this with my finger. Okay, so I place my first finger here, it sounds like this. I place it here, it sounds, and of course when I go even nearer, it sounds like this. Okay, and if you do realize, you can distinguish the frequency. The frequency actually increases, okay, as I shorten the length. Okay, so okay, maybe the first string is not so pleasant to the ear. This time I'm gonna play the second string and the third. Okay, and for all the strings, you do realize that the shorter the length, okay, that is the length of play, okay, the higher the frequency. And so the length of the string and the frequency or the pitch of the sound wave, okay, they are inversely proportional to one another. And do realize something that, okay, so for each of the string they have different sound, and if you are good, okay, you actually can listen that they are of different frequency, and particularly the first and the last string. Okay, so for the first and the last string, you can hear a distinct sound. Okay, so this being at a high frequency, I mean at lower frequency, okay, it's low, the pitch is low, so frequency is low. But for the last string, okay, the pitch is high, the frequency is high. And the difference between these two strings, if you can realize that, is that this string, the first string, is thick, okay, while the second string is so thin it is barely visible here in this video. Okay, but of course it's visible, right? Okay, so for thicker strings, their frequency is much lower than thinner strings. Okay, so thickness is inversely proportional as well. The thicker you are, the lower your frequency. Okay, and the last one is about the tuning of the guitar. Okay, tuning this, right, will make this string either tighter or having less tension, that is looser. Okay, so I'm going to tune just a bit. Okay, now I don't want to tune too much, otherwise it's quite troublesome. Okay, so I'm just going to show you all a little bit. Okay, first I want you all to listen to this now. Okay, so this is distinct enough. Okay, and I'm going to make it tighter now. Okay, okay, and I'm going to make it looser now. Okay, tighter now, and looser. Okay, so you do realize that when it's looser, okay, the string actually plays at a much lower tone. Okay, that is, the lesser the tension, the lower the frequency. Okay, so, and of course the higher the tension, the higher the frequency. That is when it's tighter, the sound actually sounds at a higher frequency, there is higher pitch. Okay, so I hope you all have seen from the video, and therefore I think it's quite straightforward, these blanks. So early on we talked about tension. Tension is about how tight or how loose the string is, and of course the lower the tension to produce lower pitch. Alright, so higher tension, the tighter it is, the higher the pitch, and therefore higher the frequency. Okay, so of course vice versa is true, right? And for length, if you do realize, the longer the length, so when the guitar string was played with this length versus a shorter length, you realize this is higher and this is lower. Okay, so longer L to produce lower pitch. Alright, and of course the opposite is true, so shorter L to produce lower pitch. Okay, so in this case, you may want to write this. Let's denote P as pitch. Alright, then T is directly proportional to pitch. L is inversely proportionate to pitch. Okay, and for mass per unit length, you realize, sorry, can you cancel this? Okay, so for mass per unit length, it's about talking about for 1 cm how heavy is that string. So you do realize that in the video, the top string is heavier than the lower string, right? And the top string plays at a lower frequency or at lower pitch than the one at the bottom. So greater mass per unit length. So okay, greater mass per length to produce a lower pitch. So for this, let's just call this M. Okay, so M is in this case inversely proportional to P as well. Alright, so yeah, this is for guitar. Okay, and I hope you kind of understand what's going on. Now I'm going to talk a bit about length. Okay, and it has relation to the case of a tuning fork. Now when we look at longer and shorter tuning fork, right, later on I'll post a link on tuning fork also, so you may want to read about what's happening in detail. Okay, so basically I'm going to summarize what that length says. Okay, so for the reason why a longer length produce a lower pitch, right? So if we have V equal F lambda and V is constant, right? In other words, if F increases, then you know lambda must decrease, and the opposite is true. So if F decreases, then lambda must increase. Now this relation is true, and hence for a longer string, you do realize that they have more space to vibrate. Having more space to vibrate, right, might mean that, having more space to vibrate as compared to this, okay, will mean that this will have a longer wavelength. Okay, because they have more space to vibrate. Having a longer wavelength will also mean that they will have a lower frequency. Now for this case, because they have less space to vibrate, and therefore they will have a shorter wavelength and therefore a higher frequency. And that is the case for the length. So if you do realize, when the length is longer, okay, so from here to here it's longer versus from here to here is shorter. Okay, I have more room to complete one wavelength, whereas for scenario 2, I have lesser room to complete one wavelength. Okay, so of course, therefore the longer the string is, okay, the longer the wavelength. Alright, and this is true for tuning fork also. So for a longer tuning fork, you expect that they have a longer wavelength, and if they have a longer wavelength, they must have a lower frequency. For shorter, because the amount of space to vibrate to produce one wavelength is lesser, so they have a shorter wavelength and therefore a higher frequency. In all this, right, we are assuming something. We are assuming that V is constant. That is, in air, it's approximately 33 meter per second. Okay. Yeah, and finally, just to summarize, high frequency and high pitch will always result in a So you see for the tuning fork, right, there's an inverse relation, and the relation is lambda is inversely proportionate to frequency, right? So for high frequency you get high pitch, but whenever there's a high frequency you will get a short wavelength. Alright, and this summarizes the pitch of tuning fork and guitar. Okay, and next we'll move on to the applications, the questions regarding this chapter. Now in example 2, okay, please check it out. Okay, please take some moment to do. Okay, I'm gonna write the answer down, so maybe you want to pause the video at this moment. Okay, then try out the question before you look at the answers. So double the loudness will mean double the amplitude, so it will look something like, I'm sorry, there's not enough space, but okay, it should look something like this. And double the pitch will therefore mean greater frequency, so it will finish the wave twice as fast. So something like this. Okay, and finally, can you please also look at the link below on how resonance works? Okay, there are two links with respect to resonance. Okay, it's not in syllabus, so for those who are not really interested, please at least take a look at the bridge. Okay, how the bridge collects. For those who are interested, please take a look at how resonance works. Okay, so with this I actually end the entire chapter on sound. If there are any questions, you can raise your questions either in class or personally to me. Okay, thank you for watching. Bye bye.